Hi everyone. In this lesson, we're going to look at a few applications of the dot and cross product. So let's get started. Bit of a warm-up question to begin, and you can just do this on a separate piece of paper. We learned about the cross product in our last lesson. Can you find the cross product of those two vectors? 2 minus 1, 3, and minus 6, 3 minus 9. So if you want to pause the video and give that a try, unpause when you're ready, or you can follow along with me. So I'm using the little vertical array shortcut we learned last lesson. And then we do this cross multiplication. So 9 minus 9, I get 0. Negative 18, subtract negative 18. Negative 18 also gives me a 0. And look at this, 6 subtract 6, you get 0 as well. So evidently the cross product between 2, negative 1, 3, and negative 6, 3, minus 9 is the 0 vector, 0, 0, 0. So how can this be? Because weren't two vectors, didn't the cross product give us some vector perpendicular to both? Well, it does, but consider, guys, what if those two vectors are collinear? Like this one here. Imagine taking two pens and lining them like that. If I ask you for a vector perpendicular to these guys, or say, I'll just use my pen because it's the same direction as both. There's infinitely many solutions, because any vector, like I'm rotating my pen, the second pen around my first pen, any of these vectors is perpendicular to that line. And so there's no one unique vector perpendicular to both, or no one unique direction. So the cross product breaks down. We don't expect it to give us a meaningful answer. And so it gives us 0, 0. And giving us 0, 0 ensures that, because remember this property that U dotted with its cross product, U cross V, had to be 0, right? Well, if U cross V is the 0 vector, then that gives you 0. So interesting little problem there. So there is an idea to this, is that if you take a vector A and you cross it with a scalar multiple of itself, you are going to get the 0 vector. And that's just a property you can have in your back pocket moving forward. It might show up now and then. Okay, so today we're talking about some applications of the dot and cross product. So the first is a physics application. So you may have heard about torque. Most people have experience with torque. You know, if you've ever opened up a door, you have experience with torque. You know, when you're opening a door, most people push on the door by the door handle, like the edge of the door. Nobody really pushes towards the hinges of the door. It's really hard to open a door that way. So that's the idea. You provide the same amount of force by applying, you know, a large force a little bit away from the pivot point, as if you applied a small force far away from the pivot point. Most people like, maybe you haven't changed a tire before, but you know, changing a tire is sometimes cracking those, the bolts can be pretty difficult. So if you had, say, a tire iron, you know, if you had a really stubborn nut to crack here, you wouldn't push down midway through the tire iron. You give a huge push right at the end, maybe even a big kick. So this idea of torque is useful in a lot of applications, and it's related to cross product. So a couple notes here. So the torque I should first say what torque is equal to. It's variable. So torque, we use the Greek letter tau to represent torque. Kind of looks like that. And torque is a vector. And torque is the cross product between kind of the vector representing the, like if you have a tire iron or something, R is like represents that. It represents a vector going from the pivot point to where you're applying the force, and vector F represents the force. And that's the first little note there. Second note is that the magnitude of torque is equal to, and if you recall, we derived a way to find the magnitude of the cross product in our last lesson. The magnitude of this would be, it's the size of R times the size of F times the sine of the angle between them. So it's equal to size of R times size of F times the sine of the angle between them. Now, if you look at the units, R is like a displacement, meters, and F is a force, newtons. So if you multiply those two together, the units are the Newton meter. Now, you guys have learned in physics that Newton meters are equivalent to joules if you just plug in all the kilograms, meters, and seconds. However, when we use joules to talk about energy or work, the transfer of energy, torque is actually a vector. So a lot of times when we talk about torque, we'll use the units of Newton meters because it's a vector. With energy, work, since it's a scalar, often we use joules for that. So let's do an example. So here we're using a wrench to tighten a bolt. And so we've got our wrench here, we're applying a force at the end, and you can see that the force is being applied at an 80-degree angle to the wrench. And you can see R, the direction of R, goes from the pivot point to where you're applying the force. And we're applying the force down and to the right here, and hopefully going to loosen up this bolt. So let us calculate the magnitude and direction of this torque. So the magnitude will be easy. The magnitude of the torque, the size or that displacement R, times the magnitude of the force, times the sine of the angle between them. And if you laid these two guys tail to tail, the angle between them is also 80 degrees. So we have 20 centimeters. Now you need to be careful here. The units of torque are Newton meters. So you need to have that in meters, 0.2 meters times 60 newtons times the sine of 80. And what do we get? 0.2 times 60 times sine 80, about 11.8 Newton meters of torque. All right, now which direction will this torque vector be in? So we have to use our right hand rule. So we're doing R cross F, right? So here's R, and here is the force vector, and here is R. Might be easier if you visualize F being up here, some different F, let's say, and used your right hand rule. Then, remember our right hand rule was we're going to make R our palm and curve our fingers towards the second vector. So if I take R, my fingers, and I curve them up to this dashed line, my cross product would be pointing up. But actually in this case, I'm going the other way. So R cross F is actually going to be going down. And in this case, it'd be kind of like the direction is into our page in this particular example. If some of you guys might not be so mechanically inclined, but you might have heard of the lefty loosey, righty tighty. If you can imagine the wrench being in this direction, this is actually tightening the bolt, which would make sense, applying the torque into whatever it's being drilled into, so into our page here. But it is tightening the bolt. Talking about part B, we don't have to write anything down here. But let's say I had a flat tire, and so I was going to put little Bryden to work. So Bryden does his best, and he pushes halfway up the tire iron at an angle of 80 degrees, and he tries his best, but he doesn't, not able to crack it. So what are 3 things that Bryden can do to maximize his torque? So I'll give you a hint. The size of the torque is equal to the product of these 3 things. So how could Bryden improve on these 3 things? So if you want to pause the video and think about that, or you can just kind of listen to me. So first is Bryden pushed halfway up the tire iron. If you want to maximize the torque, you don't push halfway up something, you push at the end. It's like opening a door. You push at the edge of the door. It's like cracking a nut on a tire. You use the push at the end of the tire iron. So that's what Bryden should do. He should push at the very end. Also, angle of 80 degrees. If you think about the sine function, where is sine a maximum? Sine is a maximum of 1 when the angle is 90 degrees. So to make sine theta as big as possible, don't push at an angle of 80 degrees, push at 90 degrees and push perpendicular. And the last thing obviously could do is instead of having Bryden push, I should push, because that will increase the force. So our first example of an application of the cross product is torque. Another application is you can do vector projections with vectors in 3D. And actually, this is a really useful tool for 3D rendering and graphics, this idea of being able to do a projection in 3D. So if you recall, so we're projecting V onto U. So the projection onto U of V. And if you recall, we had a formula for doing that. And the only place the V appeared was in the top here. We do U dot V over U dot U times, so that gives us a scalar, and we multiply that by vector U. So we have everything we need. Let's calculate this vector projection. So U dot V, I might just use a square bracket here. So on the top, we will have 24. So remember, we're multiplying the components together and adding. 24 plus 2 times 3 is 6, plus 7 times 8 is 56. U dot with U gives us the magnitude squared. So 6 times 6, 36, plus 9, 8 times 8 is 64. And we'll multiply that by vector U, 638. That gives us 86 over 109, I think. Oh, I definitely regret doing the mental math here. 516, I think, but I'm just going to do this. Let me get the exact value here. So 516 over 109. That would be 258, I think. 86 times 3, 258 over 109. And 86 times 8, 688 over 109. And so this would be the vector projection. That's the exact answer. I have asked for its magnitude. So for its magnitude, the magnitude of this projection onto U of V would be the square root of those things squared, added together, 3D Pythagorean theorem. So 516 squared over 109 plus 258 over 109 squared plus 688. Why couldn't I not have chosen smaller numbers? 109 squared. So a little shortcut for the calculation. On the bottom, you're going to be adding 109 squared. That's a common denominator. We can actually pull that out of the root and root it as we go, and we get the root of, or we get 1 over 109. And then you just have to do 516 squared plus 258 squared plus 688 squared. Still a bit of work to do, but that can just make it more manageable. And I think we'll get our answer as a decimal here. We'll just approximate it, 258 squared plus 688 squared equals root it and divide by 109. So I got about 8.24 units for the size of that projection. So, I mean, nothing really new there. It's just we can do projections in 3D like we did in 2D. And this is extremely helpful for, as I said, 3D graphics, special effects, video game design. All right, the next thing we're going to look at is something called the triple scalar product. So certain situations do require a combination of dot and cross products. I'm going to show you guys an application of this triple scalar product, and this is going to be a super useful tool for us in our final unit when we talk about lines and planes and all their intersections. So the triple scalar product is just between three vectors, is a dot product then a cross product. And you don't have to worry about which one to perform first because you can't do a scalar crossed with a vector. You can only do a vector cross with a vector. So in our example with u, v, and w, we're going to do u dotted with v cross w. Well, I can't do u dot v first because that gives me a scalar, and I can't do scalar cross vector. But if I do v cross w first, that gives me a vector, and I can do u dotted with a vector. So there, the order is implied there. So let's get going. So we need to find v cross w first. And if you want to pause the video, you guys are well equipped to do all these calculations yourself, but you can follow along with me if you'd like to. So let's write out v -1 to 7, -1 again. Vector w, that's easy, just a bunch of ones. And we get -1 take away 2, -3. 2 take away 7, -5. And 7 plus 1, 8. So v crossed with w is -358. Now we can do u dotted with v cross w because this is the vector 1, 2, 3 dotted with our vector -3, 5, 8. And this gives us -3 plus 10 plus 24, 34 minus 3, we get 31. So there we go. So an example of how to calculate a triple scalar product is going to show up in a lot of places, especially if you take physics. But I'm going to show you guys one specific application right now. And then we're going to use this application in our next unit a lot. The first application we'll learn about triple scalar product is for the volume of a parallelepiped. Now, the pronunciation there, I don't know if it's parallelepiped or parallelepiped. I'm just used to saying parallelepiped, so that's how I'm going to do it. It is a rectangular prism. You can kind of think of it as like a rectangular prism that's kind of been squashed to the side a little bit. So a parallelepiped has 6 sides, and every side is a parallelogram. It's almost like a prism. It is a prism where the base is a parallelogram. So we're going to actually show that the volume of a parallelepiped is connected to the triple scalar product. So in all these situations, we're going to consider 3 vectors, and they're all lined up tail to tail. And as long as no 2 of them are collinear, they're all going to kind of point off in 3 directions in 3 space. And they're going to kind of, you can think of them forming a little 3D area if you kind of connected all the planes together. So we're going to find the volume of this guy. So our starting point is that the volume for any prism you guys learned in your grade 9 course or earlier, the volume for any prism is area of base times height. So that'll be our starting point. So volume equals area of base times height. Now, if we consider the base of our parallelepiped to be the bottom here, the base is a parallelogram, then it's a parallelogram formed between U and V. Well, if you guys recall, the area of a parallelogram formed by two vectors was actually equal to the magnitude of the cross product forming that of the two vectors forming that parallelogram. So that's a property we learned in our last lesson on the cross product. So that's the area of the base. The height of the parallelepiped, we're going to use vector W. Now, vector W doesn't represent the height itself. We'd have to use a bit of SOHCAHTOA to find this height. And this angle here, alpha, combined with cosine ratio, can help us find the height. A little bit of SOHCAHTOA gives us that it would be the size of vector W. And since h is the adjacent to alpha, cos alpha. Now, this should look familiar. This is actually the very definition of the magnitude, or it's actually just the very definition of the dot product between two vectors, where those two vectors are u cross v and w. W dotted with u cross v. So that's it. The proof actually wasn't very complicated. Now, the triple scalar product can sometimes give you a negative, right? We know that if that angle is, depending on how you choose your angle, if that angle was bigger than 90, you get a negative value. So because this triple scalar product could give you negative values, the property, to finish this off, the volume of a parallelepiped formed between three vectors is actually the magnitude of this triple scalar product. Because what could happen is, like, you could also get this volume by doing u dotted with v cross w, or v dotted with u cross w. And what you would find is you would get the same numerical value, but either one or two of those may be negative. So by taking the absolute value, it doesn't matter which one you do, you will always get or the magnitude, you always get a positive value. So this is actually the absolute value of your triple scalar product. Now that we proved that, let's, we're not going to do an example, actually. I think I leave an example for your practice questions. But this idea here, the volume of a parallelepiped, we are going to use a lot in our next unit. Parallelepiped. And that actually completes our unit on algebraic vectors. So I've given you guys a set of questions to try. As usual, if you find certain questions easy, or you think just shave it off and just do what you feel you need to do to practice and get better. I'll be posting some review and an assessment in a little bit. Hope you guys are staying well, and we'll see you soon.